Good morning. So in today's lecture, I will be discussing about electromagnetic fields due to a arbitrary moving point charge. In the last lecture, we discussed about Lienard-Bichard potential. Lienard-Bichard potential are basically the vector and scalar potential. And when we calculated the formula for Lienard-Bichard potential, we found that they are expressed in terms of the previous position of the charged particle, and we call that as a retarded position. So they are expressed in terms of the retarded position. So what we will be doing today is to find out the electric field E and the magnetic field B using Lienard-Bichard potential or retarded potential. So I will write down basically, I'll move on to that page that will give us the what we have had calculated. So these are basically the expression. So what we got using Lienard-Bichard potential was the scalar potential V as a function of R and T is given by 1 upon 4 pi epsilon 0 QC upon RC minus R dot B, and the value of A is equal to B upon C square into the V as a function of R and T. Then we have also discussed about E and B. So E and B are basically the expressed in terms of A and B. E is equal to minus gradient of B minus del A over del T, and similarly B can be written as curl of A. So we will make use of these four formula to find out the value of E and B, or rather we will use the value of B and A of Lienard-Bichard potential and substitute in the formula for E and B to find out the value of E and B. One thing we have to remember always that we have to evaluate this term appearing in both the Lienard-Bichard potential at the retarded time, that is equal to TR. So we have a charge that is moving with a velocity B, and it had a trajectory like this. This is the retarded position, and P is the point of observation or the field point. So P is the field point, and the pointing vector, sorry, the R, that means the radius vector of point of observation P is R, and the position vector of the retarded position of the charged particle when the electromagnetic signal was emitted by it is R dash, and R is basically a vector connecting the retarded position of the charge to the field point P. So therefore, by making use of simple vector formula, we can write down R dash vector to be equal to capital R plus small r vector. There should be a vector here also, and by making use of that equation, we can write down R to be equal to R minus R dash. So vector R, vector capital R is a small r vector minus small r dash vector. Similarly, if we write down TR is basically the retarded time. So that means R by C earlier than the time of observation. So TR is a T minus R over C. So if you rearrange the terms, we can write down R, capital R, to be equal to C into T minus TR. Be careful that here the value of a TR is changing while the value of a T is constant, because observation is made by the observer at the field point at a constant time, and the point P is fixed in space also. So therefore its coordinates are also fixed. Now let us move on slowly to the rigorous mathematics that we will be doing today in today's lecture. So you have to be very careful and just keep on checking each and every term, each and every equation that I am going to write in today's lecture. So gradient of B, now we have a constant QC upon 4 pi epsilon 0, and then we have a function. The differentiation of 1 over x is minus 1 over x square. So there we have minus 1 upon RC minus R dot B whole square, and then we have to differentiate it once again. So it is gradient of RC minus R dot B. So these terms will remain as it is. Now we take gradient inside the bracket. So since a C is a constant quantity, so we will write it as C times gradient of R. Be careful with mod of R and the vector R. Vector R and mod of R are two different parameters. So you have to be careful basically while working out the expression for E and B. So here C into gradient of R. R is a C into T minus TR. If you take the gradient of both sides, so gradient of R will be equal to C into gradient of T. Gradient of T will be equal to 0. So therefore, it's minus a C into gradient of TR. You can see the same thing has been written over here. Minus C into gradient of TR. So it becomes minus C square gradient of TR and minus gradient of R dot B, which is as it is. Now I will make use of the formula, that is formula number 4 given in Griffith. So that formula I have already told you that we will make use of it several times in the course. So gradient of R dot B, gradient of A dot B formula. So gradient of R dot B is R dot del into B plus B dot del into R plus R cross del cross B plus B cross del cross R. For our convenience, I have written them as term number 1, term number 2, term number 3 and term number 4. And now I will be calculating each and every term, and after the calculation is over, I'll basically substitute all those terms here to find out the value of gradient of RB, and then we will substitute it here so that we will have the value of minus gradient of B, and that will complete our 50% of the calculation for E. So R dot del, now we start with the first term here. So you see R dot del into B. What is R? It's a R vector. R vector is a small r vector minus R dash vector. So that is x minus x dash into I cap plus j minus j dash into j cap plus z minus z dash into k cap. So R and del here is a del over del x, del over del y plus k into del over del z, all the three components. So if you take the dot product of this, it becomes x minus x dash del over del x of the quantity appearing outside, that is a v, and a v is a function of tr, because all these terms has been written at the retarded time, that we have to keep in mind every time while writing these expressions. So then y minus y dash del v over del y, and then z minus z dash del v over del z. Now v is the retarded velocity, z is the present position. So we will express this as del v over del tr. So when we will write this as del v at tr divided by del tr, it is the rate of change of velocity at the retarded position as a function of retarded time. So that will be the velocity, retarded velocity at that time. And then del tr over del x, and same thing we will do for the remaining two terms also. After doing this, you take out del v over del tr common. When you take out del v over del tr common, what is del v over del tr? It is the rate of change of a retarded velocity as a function of retarded time. So we will write it as the acceleration. This is also the retarded acceleration. And then whatever left inside the bracket, x minus x dash del tr over del x plus y minus y dash del tr over del y plus z minus z dash del tr over del z can be clubbed together, and we can write it as r dot gradient of tr. So therefore the first term becomes vector A, acceleration vector, with r dot gradient of tr inside the bracket. So this is the value of the first term appearing here. Here A is a del B at tr divided by del tr is the acceleration of the particle at the retarded time. The other term that we had is B dot del into r, and r is small r minus r dash, small r vector minus small r dash vector. So we will calculate now both the terms separately. So first for r and then for r dash. So if you work out whether the v dot del is vx into del over del x plus vy into del over del y plus vz into del over del z. But we have r here. When we will calculate this term, this r will come del over del x of r cap. So that will give us I cap. Then vy into del over del y of r vector. So this will give us j cap. And similarly, del over del z of r vector will give us k cap. So we will have I cap vx plus j cap vy plus k cap into vz. And finally, they will give us the velocity v. For the second term, we have r dash here. R dash is the retarded position. So again, we have to do the same thing. We have to expand this del r dash over del x to make it reasonable. We will write it as a del r dash over del tr into del tr over del y. Similarly here, del r dash over del tr into del tr over del x. Same thing in all the three terms. Then what will happen? Del r dash over del tr. This is the rate of change of retarded position of the particle with reference to the retarded time. So that is the velocity. So we will take it out, and inside the bracket we have a vx del t r over del x plus vy del t r over del y plus a vz del t r over del z. Combine them together and they become v dot gradient of tr. So our second term now becomes v minus a v into v minus a v into v dot gradient of tr. Now coming to the third term is basically slightly lengthy. So this is the part we are calculating basically curl of a v here. So curl of the velocity. So when we write down the curl, we express it in a determinant form. The first row contains basically the unit vector I, j, k. Second, the derivative del over del x, del over del y, del over del z. And the third row represents the x, y, z component of the vector whose curl we have to calculate. So now by simple method, we can find out the coefficient of I, j and k. The same thing has been done here. I into then del vz over del y minus a del vy over del z, and all the terms we can write down in the similar way, because in the next line I have not written basically the other two terms. So again, this del vz over del y is written as a del vz over del tr into del tr over del y. Similarly, this term has been written as del vy over del z. So del vy over del tr into del tr over del z, and same thing we have to do for the remaining two terms also that I have not written here. Finally, we will write these terms again in the form of a determinant. The first row I, j, k. The second row, the gradient terms I into del tr over del x plus j into del tr over del y. And the third term del tr over del z. And finally, the last term here, the last row has the acceleration component, x, y, z component of the acceleration. And therefore, we can write it as gradient of a tr cross a, this one. So a cross b is a minus b cross a. So therefore, we can write this as minus a cross gradient of tr. Now we move on to the fourth term. Again, it is the part of the fourth term, that is curl of r, similar to curl of a b. So curl of r vector can be written as curl of a small r vector minus the curl of r dash vector. So here again I, j, k, del over del x, del over del y, del over del z, x, y, z, or you can yourself predict that curl of r is always equal to 0. So the first term is 0, the second term is not equal to 0. So we will again expand this curl, that means this determinant, and we will write it as, since we have a minus sign here, so I have written the minus sign minus I cap, and then we will have del z dash over del y minus a del y dash over del z. And again, similarly, we will write down complete by writing the other two terms also. So this is now minus I cap into del z dash over del tr and del tr over del y. Again, similar to, we have done the similar thing in the while calculating the term number 2. And if you follow the same procedure, then we can write this as b cross gradient of a tr. You can verify all these things at your end to basically have a full comfort. So now we move on to the final term. We have calculated all the four values. We were calculating the value of gradient of r dot b. So this was the value of the first term. This was the value of the second term. In the third term, we basically calculated the value of curl of a b, and we got it as minus a cross gradient of tr. Similarly, in the fourth term, it was v cross curl of capital R vector, and capital R vector curl of the curl of capital R vector gives us a v cross gradient of tr. Now, in the third term and the fourth term, they are similar to a cross b cross c term. And we all know that a cross b cross c can be expanded as BAC minus CAB formula. So you can check the same thing. This is A, this is B, and this is C. So it is a B. So we have a minus sign. So minus a B into AC R dot gradient of TR. And the second is minus CAB. C is gradient of TR. Since we already have a minus sign, so this becomes a plus. Gradient of TR will be out, and we are left with R dot A inside the bracket. If you do this correctly, the first term, the two terms basically cancel out, and we are left with basically the three terms only. And the three terms are B plus gradient of TR R dot A minus B square. Now at this stage, we will need the value of gradient of TR. In the last lecture, I have already calculated the value of gradient of TR, and it was minus R vector divided by RC minus R dot B. So here I will make use of that result directly. So now let us move on to gradient of B. So gradient of B is QC upon 4 pi epsilon 0 RC minus R dot B whole square. Then we had a term C square into gradient of TR, and this is a B plus gradient of TR R dot A minus B square as it is. So we have gradient of TR here and gradient of TR here. That is why I have clubbed all the terms with the coefficient gradient of TR here. So it is a B plus gradient of TR C square minus B square plus R dot A. All the quantities inside the bracket are basically the dimension, are the scalar. So here now I substitute the value of gradient of TR. Gradient of TR was minus R upon RC minus R dot B. So that is why you have a minus sign here, and we put the value of gradient of TR. Now I have taken RC minus R dot B common, 1 over RC minus R dot B. When it comes here, in place of square, it becomes the cube. So, but the first term gets multiplied by RC minus R dot B. You see, it's a B into RC minus R dot B minus, we are left with R vector, and then inside the bracket, we have C square minus B square plus R dot A. Since we have we need basically minus gradient of B, so I have multiplied all the terms by a minus sign. So you see here, gradient of B now becomes equal to this gradient of B is the coefficient here, and then this term becomes positive R into C square minus B square plus R dot A, while the first term B into RC minus R dot B becomes negative. So this is the value of minus gradient of B. So this is the half of a calculation for the value of E. Now we move on to calculate basically del A over del T, because when we will combine minus gradient of B and minus del A over del T, then only we will be in a position to find out the final value of E. So if you see the expression for A was equal to mu 0 upon 4 pi QBC upon RC minus R dot B. So if we multiply it by C square, R epsilon 0 here and epsilon 0 here, so mu naught epsilon naught becomes 1 over C square, and 1 over C square with this C will give us an C, additional C in the denominator. So it's a Q upon 4 pi epsilon 0 C, the vector B divided by RC minus R dot B. The calculation of del A over del T is relatively simpler, but we have to be careful. So here Q upon 4 pi epsilon 0 is a constant quantity. So it is nothing but a differentiation with reference to basically T of this quantity, that is V upon RC minus R dot V. Since all these terms, velocity, R, they are expressed in terms of a TR, so it's better to write this differentiation del A over del T as a del A over del TR into del TR over del T. The same thing has been done here. So we are differentiating this with reference to TR and finally adding del TR over del T here that we have already calculated. So the first function, differentiation of first is del V over del TR, that will give us the acceleration, and 1 over RC minus R dot V term as it is. So I am basically treating it as a product of the two functions. So the differentiation of the first function into the second function as it is. Now I will retain the first function as it is and differentiate the first function. So this V, now V as it is, differentiation of 1 over X is minus 1 over X square. So minus 1 over RC minus R dot V square, and then del over del TR of RC minus R dot V. If you go inside the bracket, C is a constant quantity, so it becomes a C into del R over del TR. R is the mod of R. Then if you expand the second one, it is del over del TR of the dot product of the two functions, and you already know that the differentiation of the dot product of the two function is first function into the differentiation of second plus second function into differentiation of first. We have to maintain the order. Even if we don't maintain the order, since the dot product A dot B is B dot A, so that will hardly make any change. So C into del R over del TR minus differentiation of first is del R over del TR, B as it is, and the second term, then the first term as it is, and differentiation of second term is del B over del TR. Now here del R over del TR, when we calculated the value of a del TR over del T, we calculated the value of a del R over del TR. You will have to check the last lecture. I have written the value here. The value comes out to be del R over del TR that we calculated last time was equal to minus R cap dot B. And we made use of this del R over del TR to calculate del TR over del T, that came out to be RC upon R dot B. So you have to check and make use of basically the same function here. So if you look at this, Q upon 4 pi epsilon 0, A upon RC minus R dot B minus V upon RC minus R dot B whole square minus C into, in place of R dash, I have written vector R upon R into B. So this is the value of a del R over del TR with a minus sign, because minus sign appears with the expression for del R over del TR. Here, the second term here, in fact, I have used minus B here. You have to understand why minus B. This term here, you see that we have minus del R over del TR. What is R? We have vector R here. So vector R is small r vector minus small r dash vector. So if you replace this R vector, capital R vector, and small r vector minus small r dash vector, so the differentiation of a del R over del TR will give us 0, because the point of observation or the field point is fixed. Only the source point is changing its position. So del R over del TR, del small r over del TR will be equal to 0. And the second term, del minus del R dash over del TR. So we will have a minus velocity. So that is why we have minus, and minus gives us a plus. So this B is nothing but minus del R dash upon del TR. Minus is coming from here. So you see we have a minus sign. So minus R gives us plus R dash. That is why we have the velocity, and V dot V becomes V square. Similarly, R dot del V over del TR is straightforward. It is R dot A. So minus R dot A, and del TR over del T is again now equal to RC upon RC minus R dot V. So I have made the substitution for del TR over del T also. So that is RC. So that is why you see here C cancels out, and QR upon 4 pi epsilon 0. then 1 RC minus R dot B will come from del TR over del T. So that is here. At the same time, we take 1 upon RC minus R dot B whole square common. So it becomes QR upon 4 pi epsilon 0 RC minus R dot B whole cube, and then A multiplied by RC minus R dot B minus V, and then minus C into R dot B over R plus a V square minus R dot A. All the terms are written. We now have, so we will put a minus sign now because this is the value of del A over del T. So now we will include a minus sign. So minus del A over del T here. So minus del A over del T is now QR upon 4 pi epsilon 0 RC minus R dot B whole cube, and minus ARC plus AR dot B plus V minus C upon R dot B plus V square minus R dot A. I have named these numbers as again 1, 2, 3. Now I have written, basically copied gradient of B also here. Gradient of B that we calculated was QC upon 4 pi epsilon 0 RC minus R dot B cube. So we have R here and here we have C. So if we want to put them together, it's better to equalize basically the coefficient of both the terms with the quantity inside the bracket. So I will make the changes in gradient of B. What I am doing, I am multiplying and dividing it by R. So I have R here, and you can see in denominator with every term we have an additional R here. Similarly, we had a C here. C now goes inside. You can see C here, C is here, C is here, C is here, and C is here. C is with all the terms. So now the coefficient of the gradient del A over del T and gradient of B terms is the same. So now we can play with the terms inside the bracket. Now here, if you put them together, you will find out the first term, term number 1, term number 2. I have called this as term number 3. I have called this as term number 4. These two terms are term number 5, and then plus a B square into B, and this R and R cancels out. C into C becomes a C square. So minus C square into the velocity. So you will see further that I will club B square minus C square into the velocity, and I will call it as term number 6. So if you put them together to find out the value of electric field vector E, so E is now minus gradient of B minus del A over del T. So when we will put together, one term drops out, one term cancels out. This term cut with red pen, and this term they basically drops out, and we are left with now 1, 2, 3, 4, 5, and one term that I have basically just marked. I have not written term number 6 together. So now in the next line, I will write down all these terms here. You can see ARC is the first term, plus AR dot B is the second term, minus B into R dot A is the third term. Here I have maintained the order, and here I have named them because they are now as per the order written over here. Similarly, we have, you can see here, we have the fourth term R dot, so 3 term, then R dot C upon R, R into R dot A. Fifth term is a C upon R. You can see this term, this fifth C upon R is common. R is also common, and then inside the bracket we are left with C square minus B square. So this is C square minus B square, and then the sixth term that I have not named here, that can also be written as R and R cancels out. So it is vector B and then B square minus C square. Now there are several ways of working with the equation for E and B. We can basically put the fifth and sixth terms together. We can put the third and fourth term together also, and then I think it will be more easier for us to understand the expression for the value of E. In the textbook, you will find that they write down the value of E as Q upon 4570 that we have here. Then R upon RC minus R dot B whole cube, they write it to be equal to R upon R dot U whole cube. U is defined as CR cap minus B. So if you find out R dot U, it comes out to be RC minus R dot B, because R dot R gives us R square and R square upon R will give us 1R. So R dot U is RC minus R dot B. So that is similar to the denominator here. So we have R upon R dot U whole cube. Inside a bracket, all these 6 terms or 5 terms are the 3 terms. 3 terms means if you club 3 and 4 together, 5 and 6 together, so then we are left with basically 3 terms only. And we can club all these terms in the following fashion: U into C square minus B square plus R cross U cross A. Let us see how do we do this. So just remember all these terms of E here. So what I will do on the next page, I will write down first term as it is. Maybe the first term here becomes equal to, if you look at the first and the second term, if I pull out A from here, so it becomes A into RC, R dot B minus RC. So R dot B minus RC is basically minus R dot U. So I will be doing the same thing on the next page. We will make use of all these expressions here. This is whatever I have done inside a bracket. That is other way of checking that R cross A cross U is similar to what we got, but we have a direct method also. So we calculated basically all the 6 terms here. So this is minus A into RC minus R dot B. Now the third and the fourth terms together, third and fourth term is R dot A and then CR upon R minus B. And then fifth and sixth term together, C square minus B square is common, and we will be left with C into R cap minus vector B. Now with U, as U is our U here is C into R cap minus B, or C into R vector upon mod of R minus B, because velocity is a vector. So we have basically a unit vector with the velocity of light, and B is a vector, so it is the difference of the 2 vectors, so therefore it's a vector quantity. So here the first term A and then R dot U, I just now showed you that R dot U can be written as RC minus R dot B. So it's a minus A and then R dot U. Similarly, R dot A and the quantity inside the bracket can be written as vector U. And similarly, what we have here with C square minus B square can also be written as vector U. Now we know the formula. In fact, we are going back now. A cross B cross C. A cross B cross C is CAB, sorry, BAC minus CAB. Here we are going to club the first and the second term together. So if you club the 2 terms together, it's better to see the reverse way. R cross U cross A. R cross U cross A can be visualized as A cross B cross C. So it's a BAC. So B is U. So U into R dot A is BAC minus C. C is A. So minus A into R dot U. These 2 terms can be combined together to write R cross U cross A. And the last term U into C square minus B square, that is as it is. So this way, by some practice, we can write the electric field vector as QR upon 4 pi epsilon 0 R dot U whole cube into R cross U cross A plus U into C square minus B square. If you find out some difficulty in doing this, then you can follow basically what I have done basically on the upper side of this page. I have expanded this R cross U, and the purpose of writing these numbers 1, 2, 3 and 4 was just to have one-to-one correspondence, that we can write whatever we got and whatever we are writing by expanding R cross U cross A are similar, so we can verify. So I will suggest you not to basically follow this method, just that means a verifying after expanding the cross product. It's a better that you work out directly and club the 2 terms together BAC minus CAB together as A cross B cross C, and you will be able to write down the value of the electric field E to be equal to QR upon 4 pi epsilon 0 R dot U whole cube. And then inside the bracket, we have R cross U cross A plus U and then C square minus B square. Same thing we have to do for the magnetic field also, because this is the expression for the electric field. Remember here also R, U and A, they all correspond to the retarded position, that is still there. Now B is equal to curl of A. We have already expressed A as a V times B scalar vector upon C square. So it's velocity vector times the scalar vector, scalar potential divided by C square. So now since B now 1 over C square is a constant quantity, so that we can take it out, and then we are left with basically the curl of the product of a scalar quantity and a vector quantity. So if you expand it by applying an identity in vector calculus, we can write it as a V and then in the bracket curl of B minus a V cross gradient of the potential. Again, now we will calculate all these terms. Here our life is simpler because we have already calculated the value of curl of a B in the first half of in the previous calculation. So I have copied it as it is. It is a 1 upon 4 pi epsilon 0 QC upon RC minus R dot B and then minus A cross gradient of TR. Minus B cross, we have calculated the value of gradient of a B also, but be careful when you substitute all these values. So if you see here, we have minus a B cross, there is a coefficient QC upon 4 pi epsilon 0 RC minus R dot B whole cube, and then we had inside the bracket RC minus R dot B into vector B minus R into C square minus B square plus R dot A. In the first term, I will substitute the value of gradient of TR. Gradient of TR, we all remember that it's vector R upon RC minus R dot B. That is the value of gradient of TR. So I will substitute that value here. Then here we have a V cross. If you will take the cross product of this velocity vector with the terms appearing inside the bracket, then B cross B will be equal to 0, and hence there will not be any contribution from the first term. The contribution will come from the second term only. Inside a bracket we have a scalar quantity because dot product is scalar. So we will have minus a V cross vector R. So here gradient of TR is R vector R divided by RC minus R dot B. So since I am taking basically this RC minus R dot B whole cube common, so 1 over RC minus R dot B will come from here, and 1 over RC minus R dot B is here, so it becomes a square. Since I am taking it out, that is the cube. So RC minus R dot B will appear with this. It is minus A cross R. This is minus A cross R. That is the value of A cross gradient of TR. So gradient of TR is R. So it becomes A cross R. Why a plus sign? Because in gradient of TR we have minus R upon minus R. This is the value minus R upon RC minus R dot B. So because of the minus sign here, we have basically plus this minus, and this minus becomes a plus, and we have A cross R, that is plus. And the other term, this term drops out, B cross B is equal to 0. We have minus B and minus R. So that also essentially gives us a B cross R with a plus sign, and you can see here, B cross R. Now I am taking a minus sign out. So when we will take a minus sign I have taken out based on the ground that A cross B is minus B cross A. So this is A cross R. So if I write it as R cross A here, so there will be a minus sign. Similarly, I will take R cross B with a minus sign. So we pull out the minus sign from both the expressions. R is here and R is here. So it is R cap. Why R cap? Because I have written an additional R here. So this R divided by the R here will cancel out and give us this expression. So I have written r cap cross the quantity inside the bracket. If you check the quantity inside a bracket, we have c square minus b square, and then with the velocity v into c square minus b square, the velocity into r dot a, and the velocity into r dot u, because rc minus r dot b can be written as r dot u, and here we have the acceleration because we have inverted this. We in place of a cross r, I am writing it as r cross u with a minus sign. So r is coming out, it's a common, so it's a cross product with the whole thing inside the bracket. Now, if you look at this expression, I have written this as b is equal to 1 over c r cap cross e. If you look at the expression for e, what you will see in the expression for e, in place of a b, you will have basically u. It is u into c square minus b square, and then these two terms are clubbed together, and we write it as r cross u cross a. The purpose of b here and u here, if you replace this b to be equal to minus u, because that will not make any change, because it is the cross product with r. What is u? U is c r cap minus b. So c r cap minus b, that is the value of basically u. So even if we write down b here, r cap cross b will be equal to r cap cross minus u. So because of the cross product, even if we have a b here, we can write this as the electric field E, and B to be equal to 1 over C R cap cross E. Now if you look at this expression, B to be equal to 1 over C R cap cross E, so the magnetic field vector is perpendicular to the electric field vector. Not only perpendicular to the electric field vector, but also perpendicular to the position vector joining the field of observation to the retardation point or to the retarded position, that is r cap. So this is one result that we get out of this expression. It is B is equal to 1 over C R cross E. The same thing is there on the, so these are the two expressions that we got. One is ERT is equal to QR upon 4 pi epsilon 0, then U into C square minus B square plus R cross U cross A. There are two terms appearing in the bracket. And the secondly, we got the value of a B in terms of E, and B is equal to R cap cross E over C. So the magnetic field of a point charge is always perpendicular to the electric field, not only perpendicular to the electric field, but also perpendicular to the separation vector or separation distance vector from the retarded point source to the field point, and that is given by R. The other important thing about this expression is, now let us check whether the expression is applicable for the static condition for electrostatics or not. So we put back the value of a B to be equal to 0 and the A is equal to 0. That means we have a static case. So if you look at the expression carefully, when B is equal to 0 and A is equal to 0, A is equal to 0 directly gives the first term, the second term here, R cross U cross A becomes equal to 0. So since B is equal to 0, so only the first term U into C square will survive, and U is also equal to C R cap minus B. So since B is equal to 0, only C R cap will be the factor that will be left here. So I have written all those terms here. This is C R cap. So I have written it as C R vector upon R. So if you put all these terms here, you will get back the expression for the electric field for a static charge given by the Coulomb's law, 1 upon 4 pi epsilon 0 q r vector over r cube, r 1 upon 4 pi epsilon 0 q upon r square. That is the magnitude of the electric force, electric field due to a point charge, due to a static point charge at a distance r. Now you further look at the results that we have calculated for the E and B. There are two terms appearing in this. One is u into c square minus b square. If you look at both the terms, then outside the bracket we have 1 upon 4 pi q upon 4 pi epsilon 0. That is basically that doesn't depend upon the value of r. Then we have r. So r will have r, and denominator r dot u, if you expand in terms of r, it will give us r cube. So r upon r cube will give us r square. Inside the bracket we have u here. So u depends upon r, but there will not be any r factor. So if you find out the r dependence, so we will call basically the two terms as the velocity term and the electric field term, and the velocity field and the acceleration field, because the first term is dictated by the velocity of the particle, while the second term is dictated by the acceleration of the particle. So the first term depends upon the velocity and it depends upon the distance as 1 over r square. But if you look at the second term, that we call it as an acceleration term, we have u cross r cross a. If you expand it, then we will have an additional r, and that additional r will give us the dependence of the second term or the acceleration field term as 1 over r. The first term depends upon r as 1 over r square. The second term depends upon r as 1 over r. That means if you compare the two terms, the second term having 1 over r dependence dominates at the larger separation distance, that even if the distance is larger, the radiation field will dominate. So that is why we call it as a radiation field, and this radiation field is because of the acceleration term. That is why you will study in future that only accelerated point charge emits radiation. So it is because of the dominance of acceleration term, its dependence being 1 over r, it dominates basically at the larger distance also. So if you compare these results that we have got for A and for E and B, we have calculated the ratio of E over B. So ratio of E over B is basically comes out to be C, or B is equal to E upon C. The electric field and the magnetic field, they are perpendicular to each other, and they are also perpendicular to the to basically the R also. R is a vector joining the field point to the source point, or field point to the retarded position. So those things are taken care of even if we are considering the terms expression for E and B in terms of retarded position. So those properties are similar to that of electromagnetic wave. So the expressions, two expressions which we have calculated in terms of retarded position, they still maintains the behavior of electromagnetic field or behavior exhibited by electromagnetic vectors, as E and B are perpendicular to each other, and they are also perpendicular to the R. And so they are all, so it transverse electromagnetic field. So same thing we are getting here also. So remember these expressions for E and B that we have calculated in today's lecture, velocity term and the acceleration term, they are written in terms of the retarded position. So what we will be doing in the next lecture, to understand them physically, we will now convert them in terms of the present position, and then only basically the physics of the moving charges or electromagnetic fields of the moving charges will be more understandable to you. So I will stop here for today's lecture, and in the next lecture we will convert these electric field and the magnetic field vector in terms of the present position. In the meantime, I will suggest you to work it out very carefully, because this is the only lecture which is basically mathematics point of view. It's quite rigorous. You have to work out each and every terms 2-3 times, then only you will have basically the comfort of understanding the derivation of all of this. Thank you very much.